Now we move to water resources in India, not as a chapter of abundance, but as a chapter of audit, crisis, and remedy. This video will do three things in sequence. First, it will audit India's water reality, how much we have on paper and how much is actually usable. Then it will show the crisis, regional imbalance, groundwater depletion, irrigation stress, and pollution. And finally, it will move to the remedy, watershed management, community models, rainwater harvesting, and policy. This is also where geography starts touching governance directly. Start with the paradox, because this is the line that frames the whole chapter. India has only 2.4% of the world's land area, about 4% of global water resources, but supports 16% of the global population. Memorize that triad exactly. 2.4, 4, 16. It is one of the cleanest opening lines for any answer on water scarcity. And there is one more number you must hold with it. India receives roughly 4,000 cubic kilometers of precipitation annually. So the problem is not simply no water. The real problem is availability varies drastically over time and space. That distinction is important. Scarcity in India is often a management problem layered on top of a distribution problem. Now come to surface water, where most students assume abundance and stop thinking. That is a mistake. India has a total river inventory of about 10,360 rivers, if you count those longer than 1.6 kilometers. The total annual surface flow is about 1,869 cubic kilometers. But here is the real number that matters. Only around 690 cubic kilometers, roughly 32%, is actually usable. That gap between total flow and usable flow is the real geography. Now keep the basin map in your head. You can see the major systems: Indus, Yamuna, Ganga, Brahmaputra, Barak, Narmada, Tapi, Godavari, Krishna, and Kaveri. But the concentration is highly uneven. The Ganga, Brahmaputra, and Barak basins occupy only about one-third of India's land area. Yet they hold nearly 60% of total water resources. That is why India's surface water story is not a story of shortage alone. It is a story of spatial inequality and temporal variability. Now move below the surface, because the real reserve is often invisible. India's total replenishable groundwater is about 432 cubic kilometers, and the Ganga and Brahmaputra basins alone hold 46% of this resource. But availability and utilization do not match. Look at the regional pattern. Punjab, Haryana, Rajasthan, and Tamil Nadu fall into the overexploited zone. Gujarat, Maharashtra, and Uttar Pradesh sit in the moderate category. And Chhattisgarh, Odisha, and Kerala are relatively underutilized. This is where serious answers improve. The issue is not only how much groundwater exists, the issue is where it exists, where it is pumped the most, and where policy is failing to balance the two. Now ask the simplest and most revealing question. Where does the water actually go? For surface water, usage is overwhelmingly dominated by agriculture. Agriculture takes 89%, domestic use 9%, and industry just 2%. For groundwater, the dependence is even sharper. Agriculture takes 92%, industry 5%, and domestic use 3%. That one comparison explains the aquifer crisis better than a full essay. India is still fundamentally an agrarian economy. Agricultural consumption dwarfs all other sectors combined. And the key insight here is decisive. The heavier reliance on groundwater for farming is the real root of aquifer depletion. Now we come to the irrigation trap, one of the most important causal loops in Indian geography. The cycle runs like this. Green revolution leads to high-yield varieties. High-yield varieties demand high moisture. That triggers a tube well explosion. And that leads straight to aquifer depletion. The numbers make it sharper. In Punjab, about 76.1% of irrigated area depends on tube wells. In Haryana, the reliance is about 51.3%. And the net irrigated area is above 85% in these states. The result is brutal. The granaries of India succeeded in rice and wheat production, but at the cost of groundwater tables. And the final phrase on the slide must be understood, not just repeated. They are mining fossil water. Fossil water means ancient groundwater accumulated over geological time, not something that gets quickly recharged every monsoon. So this is not ordinary extraction. It is liquidation of a long-term reserve. Now the crisis shifts from quantity to quality. Water pollution in India can be reduced to three major sources. First, agricultural pollution, fertilizers, insecticides, and runoff. Second, domestic pollution, solid waste, liquid waste, and what the slide calls cultural runoff, meaning waste generated by social and ritual activity near water bodies. Third, industrial pollution, chemical effluents, and heavy metals. Now connect that with river flow. Pollution concentration rises when river flow falls. That is why summer often becomes the season of peak pollution concentration. Lower flow means lower dilution. This is where many students answer mechanically. They list sources of pollution but forget the seasonal logic. Low flow is not a background detail. It is what intensifies the damage. Now map the pollution geographically. Most aspirants stop at the Ganga, and that is exactly why their answers look incomplete. Yes, the Yamuna stretch from Delhi to Etawah is critically polluted. Yes, the Ganga around Kanpur and Varanasi is a major polluted corridor. But the map also marks regional rivers that matter. Sabarmati at Ahmedabad, Musi at Hyderabad, and Vaigai at Madurai. That is how geographical awareness is demonstrated. Not by repeating one national example, but by showing that the water crisis is pan-Indian and regionally differentiated. Now map the pollution geographically. Most aspirants stop at the Ganga, and that is exactly why their answers look incomplete. Yes, the Yamuna stretch from Delhi to Etawah is critically polluted. Yes, the Ganga around Kanpur and Varanasi is a major polluted corridor. But the map also marks regional rivers that matter. Sabarmati at Ahmedabad, Musi at Hyderabad, and Vaigai at Madurai. That is how geographical awareness is demonstrated. Not by repeating one national example, but by showing that the water crisis is pan-Indian and regionally differentiated. Now groundwater pollution, the quieter crisis. Two names are non-negotiable here: fluoride and arsenic. Fluoride contamination is associated here with Rajasthan and Maharashtra. And the cause is clear. Over-extraction concentrates natural minerals. Arsenic contamination is associated with West Bengal and Bihar. The cause is described as geogenic sources exacerbated by pumping. Geogenic simply means the contaminant originates from the natural geological setting, not from direct industrial dumping. But excessive pumping disturbs the system and worsens exposure. This is the line you should remember. Over-extraction does not just lower the water level, it also degrades water quality. Now the legislative side and the uncomfortable truth behind it. The formal framework exists. 1974 brought the Water Prevention and Control of Pollution Act. 1977 brought the Water Cess Act. 1986 brought the Environment Protection Act. So the legal architecture is not absent. The problem is enforcement. That is why the central stamp here is so blunt. Ineffective enforcement. And the reality check drives it home. Even by 1997, despite these laws, 251 major polluting industries were found operating directly along riverbanks. This is where answers become sharper. Do not write lack of laws. Write implementation failure, regulatory weakness, and poor enforcement capacity. Now we turn from diagnosis to solution. The framework here is integrated watershed management. The definition is simple but powerful. It means balancing natural resources, land, water, and plants, with societal needs. And notice how the model works by linking specific problems to specific responses. Land degradation is met through channel correction. That means improving and stabilizing stream channels so erosion and damage are reduced. Water scarcity is addressed through water harvesting and check dams. Forest depletion is met by afforestation. And all three flow into one common framework: integrated watershed management. This is the critical concept. Serious water management is not one intervention. It is a coordinated land, water, vegetation strategy. Now bring in the human factor. Community participation. Three models are highlighted here, and each represents a different style of success. First, Haryali, a central government initiative. It is Gram Panchayat led and focuses on conserving water for drinking, irrigation, and fisheries. Second, Niru Miru. The phrase means water and you. Its practical focus was on dugout ponds and check dams. Third, the Arvari Pani Sansad model in Alwar district. The key intervention here was the construction of johars. A johar is essentially a traditional water harvesting structure, usually an earthen check dam or small embankment used to capture rainwater and recharge groundwater. This is what toppers do in mains. They do not stop at theory. They attach one working model to every major solution. Now the most practical remedy of all: rainwater harvesting. The modern version shown here is rooftop harvesting. Rain falls on the roof, passes through a filtration system, and is stored in a collection tank. Alongside it is the traditional tanka. A tanka is an underground or semi-underground storage structure used especially in dry regions to collect and store rainwater. Now do not treat this as a small household measure. Its effects are much larger. It increases water availability and saves pumping energy. It helps prevent saltwater intrusion in coastal areas. And it can even dilute contaminants like fluoride and nitrates by improving recharge and freshwater balance. That is why this is marked as a critical concept. Rainwater harvesting is not just storage. It is recharge, protection, and quality improvement. Now close with the policy hierarchy, because this is where geography enters constitutional reasoning. Under the National Water Policy 2002, the order of priority is clear. Priority 1 is drinking water for humans and animals. Then comes irrigation, then hydropower, and after that, navigation and industrial use. You must remember that hierarchy exactly. It keeps returning in both prelims and mains. Now add the policy directives. Groundwater exploitation must be regulated. Irrigation projects must include a mandatory drinking water component. And the system must rely on education, regulation, and incentives. And this is where the best answers make the final leap. Link the top priority, drinking water, to the right to life under Article 21. Because once water is framed as a life right, it stops being only a resource question. It becomes a governance and justice question. If you have understood everything we covered, you are exam ready.